Suppose we have a finite simple graph. So graph consists of vertices and edges, and by simple we mean that between any two vertices there is only a single edge possible, and we are considering undirected graph, so there is no direction attached with edges. So for example, if we take three vertices 1, 2 and 3, and suppose this is our graph, we have an edge from 1 to 2 and an edge from 2 to 3, and suppose we also take an edge from 1 to 3. Now with a graph we can attach a matrix called adjacency matrix of the graph, and this matrix is defined as follows. In this matrix, ijth element is 1 if there is an edge from I to j, and otherwise it is 0. So if we look at the 1th element of this matrix, then we have to ask if there is an edge from 1 to itself. No, there is no edge, so this element is 0. If we look at the element at position 1, 2, then we have to ask if there is an edge from 1 to 2. There is an edge, so this element is 1. If there is an edge from 1 to 3, yes, so this element is again 1. Is there an edge from 2 to 1? Yes. From 2 to itself? No. From 2 to 3? Yes. From 3 to 1? Yes. From 3 to 2? Yes. And from 3 to itself? No. So this is our adjacency matrix of this graph. Now this matrix has a very beautiful property. If we take its nth power and consider its ijth element, then this is equal to the number of paths from vertex I to j of length n. So number of paths of length n from vertex I to j is given by ijth element of the nth power of adjacency matrix. For example, this first power itself gives the number of paths in the given graph. So there are 0 number of paths from vertex 1 to itself of length 1 if we consider first power of a. Then there is no path of length 1 from vertex 1 to itself, so this element is 0. There is one path of length 1 from vertex 1 to 2, so this element is 1. That is number of paths of length 1 from vertex 1 to 2. And there is one path of length 1. Length 1 means there should be only one edge involved. So there is only one path of length 1 from vertex 1 to 3. So this element is also 1. So this is true for the first power. Let us look at the second power of a. If we consider second power of a, then we have this matrix multiplied with itself, and this gives 2. this row multiplied with first column will give 2, then this row multiplied with second column will give 1, then again 1, then 1 2 1 1 1 and 2. So this is our second power of A. If we look at the element at position 1 1 in A square, then this is equal to 2, which means that this is a number of paths of length 2, because we are considering second power. So number of paths of length 2 from 1 to itself, from 1 to 1. If we look at this graph, then what are these paths of length 2? One path is if we go from 1 to 2 and then return to 1 along the same path. So one path is 1 to 2 and then back to 1. This is a path of length 2. And another path of length 2 is 1 to 3 and then back. So these are the only paths of length 2 from vertex 1 to itself. If we consider the element 1 2, then this is equal to 1, and this is number of paths of length 2 from 1 to 2. So number of paths of length 2 from vertex 1 to 2 is only 1, and it is clear from this graph that this path is 1 3 2. This is the only possible path of length 2 from vertex 1 to 2. So this is the only path, 1 to 3, then 3 to 2. This is the only path of length 2 from vertex 1 to 2. So number of paths of length 2 from vertex 1 to 2 is 1. So since this is a symmetric graph, for other vertices also we have the same numbers. So there are only two paths of length 2 from vertex 2 to itself, and also for vertex 3 to itself there are only two paths of length 2. If we consider the third power of A, then we have to multiply the second power again with matrix A. Zero, 1, 1, 1, 0, 1, and 1, 1, 0. So the first element will be, and this row multiplied with the first column will give 2. The element at position 1 2 will be this column multiplied with this, and this row multiplied with this column, which is 3. Then again 3 3 2 3 3 3 2. So in third power of A, the element of position 1 1 is 2, and this is number of paths of length 3 from 1 to itself. If we look at this graph, then we see that number of paths of length 3 from 1 to itself, there are two paths. One path of length 3 is 1 to 2 to 3 to 1, 1 to 2 to 3, and then to 1. This is a path of length 3 from 1 to itself, and another path of length 3 from 1 to itself is 1 to 3, then 2 and then 1. So these are the only two paths of length 3 from 1 to itself. Therefore, in the third power of A, the element at position 1 1 is 2, which is the number of paths of length 3 from 1 to itself. If we look at the 1/2th element, then this is 3, which is number of paths of length 3 from 1 to 2. So if we look at this graph, then number of paths of length 3 from 1 to 2. What is the number of paths of length 3 from 1 to 2? If we go from 1 to 2, then back to 1 and then 2, 1 to 2, then back to 1 and then 2. This is a path of length 3 from 1 to 2. Now another path of length 3 from 1 to 2. What is another path of length 3 from 1 to 2? We go from 1 to 2, then we go to 3, and then we again go to 2. So we go to from 1 to 2, then we go to 3, and then we again go to 2. And another path is we go from 1 to 3, then we go to 2, 1 to 3, then we again go to 1, 1 to 3, then again to 1, and then we go to 2. So these are the three paths of length 3 from vertex 1 to 2. First path is 1 to 2, then again back to the vertex 1, and then again to 2. Second path is from vertex 1 to 2, then from 2 to 3, and 3 to 2. This is the second path of length 3. And the third path of length 3 is 1 to 3, then back to 1, and then again to 2. So these are three paths. These are the only three paths of length 3 from vertex 1 to 2. So the number of paths of length 3 from vertex 1 to 2 is 3. Similarly, we have the same situation for other vertices. The number of paths, for example, from vertex, number of paths of length 3 from vertex 2 to 3 is again 3. Number of paths of length 3 from vertex 2 to itself is 2, and so on. So in general, if we have any simple graph, and we are considering undirected graphs in this case, then for that graph, the nth power of the adjacency matrix gives the number of paths of length n between the vertices of that graph.